Sorry about that. Please catch your breath. Don't rush. Yeah, so we will talk about young suns and their planets, modeling stellar activity in the search for emerging planetary systems.
Test. Hello. Okay, great. So, hi, I'm Shih Tang. I'm a final year grad student at Rice University, working with Professor Christopher Johns Crow and Dr. Lisa Prato at Law Observatory. So it's my pleasure here today to show my recent physical spot model and give you some preliminary results on our stellar surface retrieval for some young active stars. So in today's talk, the young active stars that I'll be mentioning is the class 2 and class 3 T-Tauri stars. So these stars are young, mostly below 10 million years old. And the reason we choose is because they have very strong magnetic field strengths, which lead us to these prominent star spots, as you can see in, let's see if I can use this. So on the surface of these T-Tauri stars, you see the prominent spots compared to our own sun is the small star spots on the surface. So because the spot is huge, it's easier for us to try to map out of them. And also, huge spots give us some issues when we're trying to do our exoplanet science and also the stellar evolutionary. And because Lucas' nice talk before, I don't need to go through the details of it now. So I'll just go through some big things here. So first thing is it will affect the exoplanet atmosphere communities because the unalkylate spots will affect the transient depth, then affect the transmission spectrum, then the atmosphere composition we get will be biased. And then as the most known one is the radial velocity effects. So spots will mimic planetary RV signals. So it's hard for us to find planets in these young stars. And finally, also, we need to consider the effect in stellar evolutionary. So if you want to like place your host star of your planet and get the age of it, right? The usual way is to estimate the effective temperature, put it on the stellar evolutionary track, and maybe estimate the age or radii, something like that. But if you just take a spectron trying to fit a single stellar template, the effective temperature might be biased because now you see there's two components on the surface. You get a cool components and a hot photosphere. So that will bias everything. So now we see it's important trying to figure out what the surface looks like of these young active stars. Before going to my model, the current most common way to do so is using the Doppler image effect here. So it's actually pretty simple, the basic of Doppler imaging, because you can imagine there's a star here, there's the model, and if you have a spot on the surface, so at the bottom here, I show you a single absorption features of a absorption line. So it's flux versus wavelength. So if the spot is coming towards, you will have a less blue shifted flux here. And then moving on the surface, the skewed features will also propagate to the red shifted side because it's away from us. So using the location of these asymmetry features, we can track the longitudinal locations, right? And the depth of this asymmetry will somehow give you the latitudinal information. So using this, it's how the Doppler imaging works. So here is an example of the Doppler imagings on the calcium-4 T-Tauri stars. If you are the first time seeing this kind of plot, here is they show you a brightness map of a top-down view. So the very center is the pole, and this is 60 degrees, 30 degrees latitude, and equator is the solid line, and below that is the southern hemisphere. And the color bar here showing the red one is darker area, so it's dark spot. Blue is hotter area, brighter area, is hot spots, right? But you will see here, there's an issue is that using this Doppler imaging, we know the number of spots, the location of the spots, but you see, it's showing as a magnitude difference, right? It's not temperature, but what we really want is the temperature. And Doppler imaging has this ambiguity in the spot size and temperature degeneracy. And also it's hard to get this photosphere temperature as well. So in order to do this magnitude stuff, the starting needs to adopt a 4100 Kelvin photosphere temperature to do so. So in order to address this, we need a temperature indicators to break this degeneracy. And then that's what we need my equivalent width ratio techniques I developed, published last year. So here is basically, if you have a star, has a big spot, right? The temperature will changing as the spot rotates on the surface. So if you find a set of temperature sensitive lines, as you can see here, the OH and iron lines are around 1.6 micron, then you can see that the line depth changes from hot to cold. So the OH line, let's see if it's working. The OH line gets deeper when it goes cooler, and the iron lines get shallower. So imagine if you take the ratio of these two lines, right? The ratio, or more robustly, the equivalent width ratio changes periodically, as you see in the bottom plot here. And meanwhile, with this model, you can also measure the radial velocity caused by the spots. Now, in order to do this kind of simulations, there's an issue is we need very high resolution spectral modeling, which is something it's lacking on the market now. So I have to do it myself. So this is the basic concept of spot modeling. You first grid your spot into different grid, right? And based on the locations and the temperature of that patch, we assign a high resolution spectrum to it. And here I not only put a high resolution spectrum, we also consider the effect of your viewing angle. So you know that if you're viewing like directly or on the side, you need to consider the actual effect. That's the mu-dependent intensity spectrums. So we don't do the easy way. The easy way is to scale the flux based on link darkening, though, which will bias the line depths at this core temperature ranges. Next is based on the location of the grid. We put Doppler shift because the star is rotating. And then if you integrate all of that, you get this high resolution spotted spectrum model and your spectrum. Now in the end, you can calculate your radial velocity, equivalent width ratio, and photometry from this model. So with this nice model, we can put this into test. So the first thing we test is the Kelvin 4, right? Because there's a lot of studies on it. So we get these stellar parameters up there. Now we also need the spot configurations. So the first easiest way to do it is estimate from the Zeeman Doppler imaging. From the Doppler imaging, you can estimate spot location, spot size, but the temperature is tricky. So if we adopt a photosphere temperature of 4,000, then we can use the log brightness here and infer it to flux difference, then estimate the temperature difference of your spots. So here is the first attempt. So here is a model. And on the right is the observable generated from the model. So on top is light curve. The middle panel is radial velocity around 1.5 micron, and the bottom is the equivalent width ratio, tracking the temperature variations. So what we can do now is overplot the observation data for the Kelvin 4, and here is the result. So you see photometry matches pretty well, but RVs and equivalent width ratio is way off, right? Which makes sense because we know that temperature is, we adopted a temperature for 1,000. So what we can do here is lower the adopted photosphere temperature and see how the results are. So just focus on the plot on the right, and you see lower 100 in photosphere, another 100 in photosphere temperature, and at 33,000 is pretty much good, right? So now at this point, we think that equivalent width ratio is actually pretty good on doing this, breaking the degeneracy. So I do a actual forward model fit with only 8 spots here. And then you can see that we're fitting the temperature of the spots, the size of the spots, and you get this nice fit here, reduced Kaiser 1.7. So here I'm just demonstrating the current working model that it is able to fit the temperature of the spots, size of the spots, and the photosphere out of it, right? Okay, and then the end of it, I just want to share that since the model can do multi-wavelengths, so here is the wavelengths we do to do the fit, right? You can actually calculate the radial velocity at different wavelengths, and this is the amplitude of the radial velocity. When you compare to the model, it actually fits pretty well. And yeah, so I will leave my summary here and take questions. Thank you.
Thank you. Questions? The one in the back? Or two that way here. Okay, so first question there and second question, Ilaria. Yeah.
Thank you, Arvind Gupta, Noir Lab. This is a really cool work you're doing. Have you tried injecting like a pure Doppler shift signal and seeing if you can recover just the spot signal without also removing the pure Doppler shift?
So yeah, that's a very interesting one. So that's the next thing we want to do with the model. So we want to try to make sure the models is working on, and next we can do a lot of things like put in the planet signals around it and all those stuff. Yeah, that's definitely next step I'm going to do. Thank you.
Question?
Thank you
Yeah.
very much. Very nice results. Ilario Pascucci, University of Arizona. I was wondering, have you investigated what is the impact of these spots on the stellar masses and ages?
Oh, can you say that again? Sorry, I didn't get it.
What is the impact of the spots on the stellar masses that you would determine? Yeah.
Okay, the impact of the stellar mass because of the spots, right? So yeah, right, I think the issue is when you compare to the evolutionary track, that's usually the case, right? And the easiest way to do it is get the affected temperature, right, and put your targets on the evolutionary track, especially young targets, right? That's how when people are trying to do it. So if you get the wrong bias affected temperature estimated, then you will get unphysical usually results on the evolutionary track. So we need to like first trying to get the best affected temperature, right? Consider the spot effect. And also on the other side is the evolutionary model part, right? Now is 1D model, the surface is homogeneous, right? But we need to actually consider spot also in the evolutionary model to make the model better. That's basically what we find here, yes. Yeah, and also it will affect the mass, right? It's always the case, yes.
Last question?
This is really great work, and I look forward to your paper. I'm curious about whether your model or whether we've seen in stars the spots actually evolving. So like on the sun, the spots shift in their location, they grow and shrink, and they change in temperature over time. Is that something that we have seen or that you could conceivably constrain with your model?
Yeah, so just based on the light curve, we already see the changes, right? The shape, everything is changing. But yes, so now I'm like conducting a survey trying to do follow up on the calcium 4, right? So we can see how like basically what we want to see the size and temperature changes, right? As a function of time, there's the short time variability and also yearly, seasonally variability. So yeah, that's something I've been proposing for observational plan to do that. Yeah, thank you.
Great. Thanks, Shih again, for a great talk.